These are the two main types of heat engine. For external combustion engine, we will study steam power plant, and for internal combustion engine, we will study two-type, rotary, and reciprocating. For steam power plant, the cycle for this one is a steam power plant. This is a cycle for generate energy by steam, and this is previously used to obtain energy, electric energy. This is the default one used before.
For vehicle.
Again?
For a vehicle.
Vehicle, vehicle, I think so. It's not start by steam. It's start, fuel, I think, by coal or something like this. All is fuel. But I took for plants for produce electricity where almost here I don't think so we have any steam power plant. This maybe you found it in countries like India, like Egypt, which more is huge because this take large space and produce normally medium amount of energy, of electricity. But nowadays we use
Thermal power.
nowadays we use a simple design and obtain energy, high energy. Like famous one is gas turbine. Almost I think here we have a lot of gas turbines here to produce energy. And also we have updated for renewable energy like solar energy, wind energy. But here for these power cycles, we will focus for the two main types for internal and external combustion engine. And we will study for external combustion engine the steam power plant, and the cycle for this one is called Rankine cycle. And the internal combustion engine like rotary and reciprocating, and we will study for rotary gas turbine, and this cycle is Brayton cycle. If you remember previous session, we studied already reversed Brayton cycle, and I tell you next session which is take it today, we will study the normal one, Brayton cycle. And I told you, Brayton cycle is the one of the important cycle coming in the exam. For reciprocating, we have petrol and diesel, petrol spark ignition engine and diesel compression ignition engine. And we will study for petrol auto cycle, and we will study other cycle is diesel cycle, and we will study one in between is dual cycle. This is a classification what we will study today. Okay. Okay. Just wait. Jig Matthew, what you need? I try to make it unmute, but something in your device, not me. Okay. Take your mic. Okay. First one is Rankine cycle. Okay, Rankine cycle. Also, it consists of 4 elements like the previous studies for refrigeration and so on. What is this 4 elements? The main 4 elements here is this steam generator, which is boiler in this cycle. Then going to turbine. Next, after turbine, we're going to condenser. And after condenser, we will go to pump. and from pump back again to the boiler. These are main four elements for this cycle. After boiler, the media is steam to turbine, then going to something mixing between steam and water, then going after condenser to be fully water liquid pure up to reach to the boiler. For boiler board, this is a part for heat added. Turbine is a part for energy produced, and condenser is the part for heat rejection. Pump is a part to increase the pressure of the water from low pressure side to high pressure side. Also, this cycle is working between two pressure sides. Same also like the same concept of refrigeration cycle. Okay, but we will know which in low working in low pressure side and which one is working in high pressure side. Okay, going to the analysis for this cycle, analysis on the diagram, analysis for the equations. Also, as I tell you, the general information for how to calculate work and heat, if you remember, I tell you it is difference between two enthalpies. Difference between two enthalpies. It means, for example, I want to work between 1 and 2. It means, just a moment, and close the door. If I work here like in turbine between 3 and 4, so the work it is equal to 2 difference between two enthalpies between 3 and 4. It means H3 minus H4. This is what we will see now. Boiler, for example, I need the heat for the boiler added, just the difference between two enthalpies before and after. It means H3 minus H2 and so on. All equivalent like this. Okay. Okay, see the diagram first to be understand what happened during this cycle. Okay. This cycle. We represent this cycle in TS diagram. Okay. At the beginning, we draw the two pressure line. Low pressure line, which is condenser, low pressure line, and the high pressure line, high pressure side during boiler. These are two lines. One for boiler side, one for condenser side. Condenser here in low pressure side, opposite for refrigeration, and refrigeration in high pressure side. Then we will put now points 1, 2, 3, 4. Bump the concept of bump increase the pressure. So point 1 in low pressure, point 2 in high pressure. This is what you'll see now here. If you want to 2, 1 to 2 from saturated liquid, this saturated liquid here, as you see, this point is fully saturated liquid. Okay, and this one of the important to be checked before you're going to the pump. Be sure no any gas, no air, no vapor, no anything like this. It is fully water. Okay. So the line, this one is represent saturated liquid. Other line here is represent for saturated steam. So we're going from the saturated liquid up to the high level or high pressure side. This 1 to 2, and the energy required for this pump, energy here required for work needed for this pump, it equal to H2 minus H1, H2 minus H1. Also be aware for the type of this process. This process is isentropic. Here, as you see, is entropy. This vertical, it means S equal constant for process from 1 to 2. for this work. So this process is isentropic, it means adiabatic and reversible. Boiler constant pressure heat added from 2 to 3, from point 2 to point 3, point 2 here, point 3 here. From this point to this point, this superheated area. In this area is steam, but in this area we can mention for this superheated vapor. Okay. This process for constant pressure heat added. So how to calculate here for the boiler energy? Also difference between two enthalpies, H3 minus H2. Turbine from 3 to 4. We're going down like this. Isentropically process also means S equal to constant, and we're going down from high pressure side to low pressure side. And during this expansion, we will obtain energy, electric energy. Okay. So this isentropic process also same like this one, typical. Condenser, it is working at low pressure side, and as you see here, is process is constant pressure heat rejected, constant pressure. It means for the process related for heat here for this cycle is constant pressure, and for the process related for the work is isentropic process. Please, if you have any question for the cycle, tell me. Okay, next. I go through for the analysis quickly. You will apply first law of thermodynamics. This is first law of thermodynamics. This total equation for first law of thermodynamics. Q minus work equal internal energy or change of internal energy. Okay, so you will apply this equation in pump, boiler, turbine, and condenser one by one, and at the end, what we will see, we will found each element is equal to difference between two enthalpies. That's it. Check it one by one quickly. Pump, for example, we will see pump here.
Sir,
H1.
what the H1 and Z1, they're not same, not height or different this one.
No,
Previous, go to previous.
here.
Yes, H and Z, not the height.
Different type of energies. Different type of energies, like potential energy, like kinetic energy, like potential energy, or mention with this flow energy.
Potential rho GH.
Rho.
Rho GH, no potential. Kinetic half MB square.
This.
Yes. And,
Which means this
and
one. This one, yes.
yes.
Yes, this potential. This related to the flow energy.
And kinetic half MB square.
Yes.
1/2 MB square.
Yes. Normally this not change. We consider as 0, and the only effect is enthalpies, internal energy for this part, which is included in internal energy plus flow energy. Okay.
Okay.
Here what is it? Work for the pump is equal to H1 minus H2 here. But what is difference between this one and this one? Difference is this one times m dot mass flow rate, which is unit is kilowatt. This without m dot, which is unit kilojoule per kilogram. That's it. Okay. We apply the same equation for all elements one by one, one by one. Next one, for example, you see next one. Boiler here. At the end, we found the final equation for boiler. This is the final equation for the boiler here, and the final equation for the boiler here. Okay.
All same, only H1, H2 different means like this.
Here, the difference between these two.
Yes.
This one is multiplied by m dot, mass flow rate, and in this case, the unit is kilowatt. But in other one, this is called specific kilojoule per kilogram, per kilogram, per each mass. This is called the specific. For example, this is specific heat. Previously, the previous slide is specific work and so on. Okay. Turbine, if you continue, we will find turbine the same. This work of turbine in the case of kilowatt, and if you don't consider this mass flow rate here in the equation, we found the specific work for the turbine, H3 minus H4, before and after. That's it. Easy, no problem. Next one, condenser, last one between 1 and the 4. 1 and the 4. So we'll found equation H1 minus H4, same like this one. This is not important for this one, just this calculation for how to calculate H4, because if you remember the cycle, I will see the cycle first.
If we change the sequence, suppose pump we put as the 2 or 1. If I put like I start from turbine 1, is there any problem?
No, but we consider you should be aware if this is 1, this 2.
Yeah.
For this means this one is equal H1 minus H2.
No.
Okay. No problem for the name of the cycle. All the same for us. Okay.
Yeah.
Last thing here important for this. For the previous slide, he just some calculation to calculate H4, because H4 it's not saturated liquid, it's not saturated vapor, and so on. It is somewhere here. This point 4. It's called in between steam and liquid. So this called this range or this point have a dryness fraction. Dryness fraction, this is the amount of gas to the total amount, because this amount here, sum of gases, steam, and sum of water, liquid. So here we have something called dryness fraction. Dryness fraction, it is the amount of this amount to the total amount. Okay? But it's not important for us. How to calculate efficiency? This is a very, very important thing for the cycle. Second thing, after first thing, how to calculate each element. Because sometimes this exam is just to bring one element. For example, turbine, because it's so difficult to bring total, just bring turbine and study like this. We have 1, 2, just calculate work, something like this, okay? Calculation for efficiency. Efficiency is equal what? As a general, output divided by input. So if we substitute this work output, which is equal to work net, equal to work turbine minus work pump, and Q added, this is what you pay, equal this Q boiler, this Q added. This is the input, Q added. Then I'm going to substitute for work turbine, work pump, and Q boiler, and we will found this is a final equation for the efficiency. But we can simplify this equation. Normally, the work of the pump, sometimes he mentioned it is small or we can neglect. So we can cancel this part, and it will be at the end the equation for the efficiency of Rankine is equal H3 minus H4 divided by H3 minus H2.
Dr. Sami?
With you?
Question regarding the work for the pump. Here we have it as an absolute. I mean, sorry, not absolute, like it's positive, yes?
Positive, because yes, this work obtained.
Okay, that's why. Okay, thank you.
Pump is negative.
Yeah.
Excuse me, sir.
Okay, boss.
So what about the heat rejected by the condenser?
Heat rejected by condenser is difference between point of, you need the equation or need the understanding for this?
No, do we consider this thing for the efficiency?
No, not consider this in during efficiency because we don't pay nothing for this. Just this condenser, it's like heat exchanger, same like the condenser for the air conditioning. The refrigerant is going
Still
to,
this heat is what we are, it's a part of the heat which we add in the generator also,
but it's
I
not
mean
actually,
in the steam generator.
actually this like heat exchanger. We have here source of external work in this case, and this was sorry, source of water, external water.
Yeah,
This water from river or whatever from sea
yeah.
is going inside to make it calm for the condenser to be saturated liquid. So we don't pay anything for this, just this one going to be heated and going out. That's it.
Hmm. Okay. Okay, sir, thank you.
Okay. So we consider in this equation only work of turbine and Q of boiler, and pump if the pump affect on the work. If not affect, we can neglect. Now we will study some effects of pressure or temperature to improve this cycle. How to improve the efficiency for this cycle. And this problems is coming theoretical, whatever, in the shape of question statement and need answer, or figure and need answer. Okay. We study effect of three parameters. First one is effect of condenser pressure. If you remember the cycle, condenser pressure is in lower one, correct? This P condenser. So what we will study for effect for this one? If this line going down, it means if we expand in the turbine more to decrease the condenser pressure, what will happen? What we'll see if this is going down like this? This is what we'll see here. If we will decrease the condenser pressure, okay, we will see at the end the expansion of the turbine increase. Expansion of the turbine increase. It means the work turbine increase, output increase. And the other side, the Q added almost increase also, but small amount. So at overall, work turbine obtain increase rather than Q boiler. So at the end, efficiency, what will happen for the efficiency? Increase because the numerator is increase. So for the effect of condenser pressure, when we decrease condenser pressure, we will see the efficiency increase. Okay. Other here point to mention here, he talk about for dryness fraction. I tell you before, dryness fraction is just to represent what is the amount of vapor to the total amount of the mass flow rate. Dryness fraction, as you see here for this one, dryness fraction here is decrease. Dryness fraction decrease. Here is this range. This here is decrease. But not focus for dryness fraction. Focus more for efficiency. But no problem to be aware for the other one. Effect of boiler pressure. Boiler pressure, actually, it is the upper one, correct? This is boiler pressure, this one. So what we will study here for this case, we will study if we increase this pressure line. For increasing boiler pressure, what we will see here for this case, we'll see also in this case, the work turbine also increase. The work turbine increase in this case, correct? And maybe the amount of heat added maybe decrease, slightly decrease, because you reach to the boiling point earlier than before first case. Because the pressure increase, it means the temperature to start to boil is increased, and the range to change it from liquid to steam, it is not a big range. So overall the efficiency increase. Overall the efficiency increase. Dryness fraction in this case also decreased. Last one, the effect of superheating. What's the meaning of the effect of superheating? Effect of superheating, it means we're going more in the superheating area. It means we need to add energy more to obtain higher degree for the output of the boiler to be more superheated. In this case, we will add Q added. Q added increase. We will add energy, heat. But on the same time, the turbine energy obtained expansion part also increase. And if you compare these two work turbine related to what happened in the heat added, we will found the work turbine is higher. So the output, still the output part is higher than the input part. So at the end, efficiency increase. Excuse me, this part. Energy increase. So you will study three types to increase the efficiency. First type, decrease condenser pressure. It means the lower pressure going to be lower more. And second way, increase the boiler pressure, means the high pressure line, just more increase. Last step or last way, superheating, increase the temperature of the output of boiler, superheating. The three ways going to be obtain high efficiency. Conclusion for that, for this chart on the right side, this chart, we'll find this efficiency here for the cycle, and this is the effect for the three parts. Superheating increase, increase efficiency. Boiler pressure increase, increase efficiency. Condenser pressure decrease, increase efficiency. Any question for this cycle? Almost finished. Question for this slide? No question? Okay. Rankine cycle modification, this is the last stage for this. We know for the previous affection, the ways, okay, how to do that. This is the Rankine cycle modification. We can do that by different ways. Increases the Rankine efficiency needs what? Need to increase this work turbine or decrease boiler or both. So this is the two main target. Increase this one or decrease this one or both. It means efficiency increase. Okay. One of this cycle is called reheat. Reheat. What is reheat? This reheat used to increase turbine work. This reheat used to increase turbine work. How to do that? What is different between these two cycles? First cycle here, for this one, I just add more heat to be obtains this point instead of this point, okay? And in this case, work turbine increase. But how to do that in the life? This is a boiler actually. Okay, this is a boiler. And for this boiler, the output going to turbine to be expanded and going out. But actually, for this one, in this case, this turbine, we don't go to expand it totally direct. What we will do, just we extract some energy from this turbine, and after that, going to expand like this here from 3 to 4, but we don't continue. No, after 4, we're going again to make reheat for this steam here, like this, by like heat exchange again with the boiler or whatever, and going again to continue expanding. So the output here for the point 4 is going here to the boiler to be heated and going out for the point 5, which is the input of the second turbine, second stage, and the output here is 0.6. So what will happen here? Just increase the expansion area, so we'll obtain more work. This function is called reheat. This function is called reheat. Clear? Okay. I think the other one, it's not here. Yes, not here. Other one I described to you quickly is called regeneration. What is regeneration? Regeneration, also we will divide turbines, something like this turbine 1. But the output, what we will use for the output? We're going here for the output, some of the output going in this side, for example, to something is called feed water heater. Okay, and then going out, I think it's condenser. Pump, and this is pump going here, going to the power. Here also we divide turbines as you see here. This turbine we extract some amount from this turbine, okay? And this amount, just as a function for this one, is make heat exchange with the flow coming from the condenser, pump, and push to boiler. What is the main function for this? To heat up this part. You remember we have two options to here before. Here, if you check the previous one, the two options, increase turbine work or decrease boiler heat, correct? So regeneration mainly will use this one to decrease boiler heat. How to decrease boiler heat? Just to support the water before going to the boiler. It means before, instead of the boiler start from the regular temperature, for example, out of the condenser to pump to the boiler at 25, for example, no, I need heat exchange with the steam from the turbine extracted here. So the temperature maybe start by 70 degree, 80 degrees, something like this, and going to the boiler. So I decrease the input of heat required to reach to the required or setting temperature for the boiler output. So we will decrease at the end, decrease boiler energy by this way. Okay, and going to expanding again for the external. And we have different types for this one. Sometimes is closed like this, sometimes it's open. Closed, it is going like this, like heat exchanger, default heat exchanger. Sometimes it's open and the mix between this one and make intermediate pressure and going with another pump to going to the boiler and so on. But overall, for Rankine cycle, how many stages we can use it as a reheat and how many stages we can use it as this one regeneration and so on. This nowadays it's working by software to be reached to the optimum output according to the input we use. For example, we can use 6 stage of turbine, for example, and during these 6 stages, intermediate between this, one going to the reheat and then regeneration and doing reheat and so on, and make a combination between this by software to obtain the optimum solution, obtain the maximum efficiency obtained, and work also of turbine. This two main advantage for the Rankine cycle. Efficiency is high, work turbine is high. Okay, before we're going to next step, I need from you, please, to give me feedback if you have any question or not. No question? Continue. Okay. Continue. Brayton cycle. This is very important cycle. Very important cycle. I tell you again, very important cycle. Coming a lot in the exam. This cycle actually is applied for gas turbine. And this consists of compressor, combustion chamber, and turbine. But as regular, we know the cycle is 4 elements. Yes, actually we have a fourth one, but in this cycle, normally it consists of three elements, but we cancel this element because it is an open cycle for applying for gas turbine exactly. But actually for as a processing of cycle, just we put here the fourth one to be a closed cycle. But for the real one, for gas turbine, is 3 element only, same like the reverse Brayton cycle applied for the aeroplane. Here, compressor, to start from this one, fresh air coming to number 2. This 2 going to combustion chamber, this air, and we will add with air fuel to make mixing here and combustion. It means from 2, then going to 3. This process is the source of heat added. Heat added. Then after 3, going to expanding during the turbine to obtain work. And as you mentioned here, what you obtain, it's not obtain work, it's work net. Why? Because the part of turbine is going directly to work the compressor itself. So what we obtain here direct, it is a work net. This is the final. Work turbine minus work compressor. Here in this cycle, we can't neglect compressor because the compressor work, it is have value. It is not a small value like bombs in the case of Rankine. No, is have a value, okay, not small. So we consider this value, work turbine minus work compressor. And the output here is exhaust gases. But normally we consider all this cycle totally as air. We consider total cycle as air, okay? So we have a difference between this cycle and the previous one. Previous one, it is steam and water. So we will calculate it enthalpy directly from the pressure and temperature according to steam tables, Molear chart, something like this. But here for ideal gas, for air, we can use it ideal gas equation. Ideal gas equation, okay? This is a closed one, same cycle, but here just represents the heat sink part. Okay, one of the important part, diagram. Here, as you see in this diagram, we will see PV diagram and TS diagram. For PV diagram, we will found 2 processes is constant pressure, which is this 2 process, Q added part, this Q added, and Q rejected. And we will found 2 other process, 1 to 2, 3 to 4, 1 expansion, 1 compression, 1 expansion, and whatever this process and this process for expansion and compression, this 2 is isentropic. This more detailed here, we can see in details. We'll see from 1 to 2, this is the compressor part is equal to constant. Entropy not change. It means isentropic process. Compressor is isentropic process. And from 3 to 4, this for turbine part, also isentropic process, no change in entropy. But from 2 to 3, this what Q added part, pressure constant. From 4 to 1, this heat rejected and it's not considered in more calculation. Okay, this is an important thing. 1 to 2, 2 to 3, 3 to 4. B. See with me this important logging for here for TS diagram. The curve it's of pressure constant. This P constant 1 for the heat rejected. This P constant 2 for Q added. You see the same constant pressure line it is close together from the part here for the temperature, low temperature and low entropy. And this, when you're going right, this range increase. This pressure like this, this pressure like this, this pressure like this. So here is small going to be more, small going to be more. You understand me? Because we will use this conclusion. Okay, going to the analysis. Analysis here. All analysis is the same previous. What's the same previous? To calculate compressor work, different enthalpies. To calculate the turbine work, different enthalpies. To calculate the Q added, different enthalpies. If you know the enthalpy after and the enthalpy before, you can calculate any element. Same. But the difference is in depth of calculation. What is it? Means that for power cycles, I tell you the enthalpy is going from tables or charts. Okay, but here, according to the media used for the Brayton cycle, this is the reason also to it's coming a lot in the exam, because it is used by regular equation without data coming from tables or from charts. You can calculate it by equation direct. What is this equation? Is related to ideal gas. If you remember when we studied thermodynamics, H is equal what? This is a function of H is a function of temperature direct, correct? Is a function of temperature direct. And is equal what? H is equal to CB T. So delta H, as very any calculation for work turbine, work compressor, Q added, Q ejected, is delta H, difference between two enthalpies, is equal what? CB delta T. So for equation related to air, gas, you can calculate delta H direct is CB delta T. And delta T is two different temperature. I know temperature before, temperature after, and CB is a constant for air, for the media. So I can calculate delta H if I know temperature. So this is the reason for this problems coming in the exam more than other cycles, because it mainly depend on the temperature. Just I given for the exam the temperature, and we can calculate it. Okay, but should be aware for the equations and some slides. What is the equation important? Equation, this one is very, very important equation. T2 by T1 is equal B2 by B1 to power gamma minus 1 over gamma. This coming from the equation of BV to power gamma equal constant. Is something related for this. Okay, but here V is constant. Here for this process, V is constant. So we'll use this one. T2 over T1 equal B2 over B1 to power gamma minus 1 over gamma. And the gamma, this is the 1.4 for the air, if you remember. 1.4 for the air. Okay. And this used where? This used for relation between one and the other. One and other. Between step 1 and step 2, for example. Step 3 and step 4. It means between the isentropic process. Isentropic what? Isentropic process. For any isentropic process, we can use this direct isentropic process. Okay. B2 over B1, it is equal to RB. What is RB? Pressure ratio. RB is a pressure ratio. It's the ratio between maximum and the minimum pressure. Maximum B2, which is the combustion chamber, okay, and the B1 is the other one for the rejection. Okay, maximum to minimum pressure. This RB, pressure ratio, pressure ratio. So we can write it T2 divided by T1 is equal to RB to power gamma minus 1 over gamma. In this case, if I give you only T1, sure, you can calculate T2 if you know B1 and B2 pressure ratio. So if you know the pressure ratio and the gamma is a constant, you can calculate direct T2 if you know T1. So H1 and H2 we know, you can calculate work of compressor. Equation for work compressor here. CB delta T is coming from the difference between two enthalpies. The same, I can multiply by m dot to obtain power. This kilowatt, this kilojoule per kilogram. Okay. Second part, pressure constant for the process for Q added. So the Q added is equal to CB delta T, T3 minus T2 or times M dot to obtain kilowatt. Third one, turbine, the same isentropic process. I can get it. The equation for work turbine here, CB delta T, CB T3 minus T4 or the other unit multiplied by M dot. Okay, but how to calculate the temperature if I don't know T1 and T2? We solve it T1 and T2. If I know T1, I can get T2 by the equation. The same equation. T2, if you know a T3, you can calculate T4 by this equation. T3 over T4 equal B3 over B4 to power gamma minus 1 over gamma. And we know B3 is B2 equal. This is a cycle here, to remember. This is a cycle. This be constant for the combustion chamber. This be constant for the rejection bar. So 1, 2, 3, 4. So 1 and 2 is almost the pressure here for the C and 4. B2 is equal B4, B3. B2 is equal B3. This is what we will do. B2, we put it B3 instead of that. B1 is equal B4. Yes. It means this one is equal to B2. This one is equal to B1. So we can B2 over B1. It is the same RB, and we can use it RB again here for this equation. Okay. Finally, this rejection, but not used a lot. Finally, how to calculate efficiency. This is an important part. Work net here, work net is equal Q net. Work net, work turbine minus work compressor. Q net is equal Q added minus Q rejected. Efficiency. What is the efficiency? Efficiency Q, it is equal to output divided by input. Output here is work net. What is input? Q added. After substitution for all these items, CB and delta T and so on, and try to make common factor and so on, we will obtain at the finally efficiency is equal to 1 minus T1 over T2. Very important equation, please. At the end for these cycles, you can calculate efficiency by easy way, T1 and T2. If, for example, he bring a question and the cycles and the many information given and so on, so on, so on, so on, but at the end just require the efficiency and the given T1 and including the many given T1 and B1, B2. So from B1 and B2, we can get it RB, pressure ratio, and from RB, make a relation between T1 and RB, we can get from this one T2. And if you are aware T1 and T2, you can get it efficiency direct without any more calculation. So this is a problem. It is easy to solve it, but be aware how to solve it, this one. If you substitute T1 over T2 by the regular equation here, yes, this one here, T1 over T2 is reciprocal because he mentioned for T1 over T2 is reciprocal for this one over RB. This is what we substitute here. Yeah, T1 over T2, 1 over RB. So efficiency, we can write it as another direct for the pressure ratio, 1 minus 1 over RB, gamma minus 1 over gamma. This is another way. The same equivalent for this one. Okay. So without any more calculation, more headache, just if you know the two pressures, you can calculate efficiency for the Brayton cycle. Two temperature or one temperature and pressure, you can calculate efficiency. This is the reason for this problem is coming a lot, because you can ask with simple given, can ask for efficiency, work compressor, work turbine, Q added, and so on. Okay. Here is the effect of pressure ratio on efficiency and power. As you see here, pressure ratio, what happened for pressure ratio? When we increase the pressure ratio, we're going to, with increasing more, we're going to obtain work net maximum up to limit. This limit is 1. But if you increase more, we're going to decrease again. So if you increase pressure ratio, work is increased up to the maximum and going back again to be increased. But for efficiency, we obtain maximum efficiency at RB maximum. And in this case, we consider this efficiency, it is a Carnot cycle, Carnot, ideal cycle. Brayton is equal Carnot. Okay, before we start this problem, just tell me if you have any question for this type of the problems. Sorry, the cycle. Any question for this cycle? Any question for this cycle? No question? Okay, if you know question, solve this problem. I write here the equation used. T2 over T1 1 P2 over P1 power gamma minus 1 over gamma, and P2 by P1 for RP, and also T3 4 by T3 for P4 minus 1 over gamma. Efficiency 1 minus T1 over T2. One thing I tell you to be close this part, temperature must be Kelvin. Try to solve it, please.
So the value of gamma air, density of air into G.
Gamma air 1.4.
Density of air and G into G.
What?
Density of air into acceleration due to gravity, rho and G. Rho of air into G. Gamma.
Why you need to calculate
1.0.
for what? Density?
Gamma.
Gamma 1.4.
1.4.
This not gamma for the m dot, not rho g. No, this is not difference. This is constant. This is not a specific weight.
1.4.
This is a ratio between specific heat at constant pressure to specific heat at constant volume. Cp over Cv. Anyone start solving? Calculate any required for work turbine, for example, Cb delta T, Q added Cb delta T for after and before, or before and after. What is Cb? Cb is equal for air 1 kilojoule per kilogram Kelvin.
Efficiency 80%.
Ready? Ready? Anyone get anything? Temperature, pressure,
Efficiency 80%.
efficiency,
80%.
80,
80.
80% for efficiency. Oh, you're going to efficiency direct by this way?
Yes.
Okay, good job. This is the end one.
Cycle efficiency.
Yes. No, we don't have answer here. We're going to answer here together. Okay, for the pressure and temperature, first in air Brayton cycle, air intercompressor. This intercompressor, 0.1 megapascal, this is P1. Temperature 15, this is T1. The pressure level of the compressor is 1 megapascal, this is P2. And the maximum temperature in the cycle, this one. What is the maximum temperature?
T2.
This one, T2?
T2.
No, actually, this T3. Check with me the cycle. We will find the cycle like this. These two pressure lines going like this. Like this. This 1, 2, 3, 4. The maximum temperature 3. After combustion chamber. Not after compressor. After combustion chamber. So this T3. In this case, we need to calculate pressure, temperature for each point. Pressure easy because T2, B2 is B3, and we have B2. It means this B2 and B3, and B1 is B4. For pressure is no problem, but for temperature we need to substitute for these two equations. T2 over T1 equals this equations to get T2, and again we apply for this equation to get T4. That's it. So we will start for first step to calculate T2 by T1 equal to B2 by B1 to power gamma minus 1 over gamma, which is equal to B2 1 megapascal divided by 0.1, which is equal 10. This at n is equal 10. 1.4 minus 1 divided by 1.4. So from this equation we can get what? T2. Please don't forget to substitute T1 Kelvin 15
Plus 20.
273. For first step, any question? No question? Okay. Second step, actually the exam not ask for all this step. The previous exam I see just coming one element. For example, it's coming turbine, coming combustion chamber, compressor. Sometimes it's coming total cycle, but ask for also one thing. Ask for work turbine, ask for efficiency, but not ask it like this for all, okay? So it's important to be aware for how to apply the equation for any point. Clear? For T4, we can write this is another equation. T4 divided by T3 is equal to B4 by B3 divided to power gamma minus 1 over gamma, which is equal to, again, B4 is the same B1, which is equal to 0.1 divided by 1 to power gamma minus 1 over gamma, and from this equation you can get T4. Other way you can use, if you calculated this one step, if you calculate this one in one step, close the door. Calculate this one in one step for the previous one. We can use it here again, okay, but just reciprocal for this one. T3 divided by T4 instead for this. So from this equation, we calculate T4. Again, don't forget to calculate T3. T3 is 1100 plus 273. Now we have all points of pressure, all points of temperature. Now we can calculate compressor work. Yes, we can calculate compressor work. Work compressor is equal Cv delta T. Which delta T? Between 1 and 2. This compressor part from 1 and 2. So T2 minus T1. Work turbine is equal to Cb delta T wind turbine from 3 to 4. So T3 minus T4. And Q added is equal to Cb delta T. Which delta T? From 2 to 3. So T3 minus T2. Now we have all work compressor turbine and Q added. What is efficiency? Just apply for this equation direct. This efficiency. Efficiency equal 1 minus T1 over T2. That's it. Any question?
P3 and P4, sir, from where?
Again, please.
P3 and P4.
Yes. B3 is the same B2 as per this chart.
P3,
Be constant.
yes. Yeah, constant.
Constantly.
Okay. Yeah, yeah.
What else?
No, خلاص.
Finish? Okay. Going to conclusions. Answer, please. Answer.
B.
B, yes, correct. Kinetic efficiency is high. Multi-stage compressor. The isothermal compression is achieved by
C, we're running compressed low speed.
yes, correct. Running compressor at very slow speed. Why multi-stage compression required? Actually, if you remember the shape of cycle, I tell you one important note. In the left side, the lines between two pressure line is slightly close together, and when going right, this line is going to be far, correct? This is a reason to use it compression in multi-stage. Why? For example, you'll see this here in details, but just I draw here to be understand what we will see. For example, if you're going from this point to this point direct, you see, this is the total required for the work compressor. But if you have intermediate lines like this, and I just compress like this here, in this way, up to the intermediate pressure, and then going again to cooling, and then going up, then cooling, then going up, then cooling, then going up. At the end, you will find the total amount of the compression here, 1, 2, 3, 4, is totally less than if you're going direct. Why? Because this line here, like this small area, but if you're going direct, is higher. So we're going to multi-stage to obtain minimum work required for compression. Minimum work required for compression. See with me here, also the same. This one from pressure 1 up to pressure 2, this is the pressure line direct. But if you're going to pressure intermediate A and then going to make cooling then continue pressure to B, then cooling to continue pressure again for final point at step 2. We'll found this part plus this part plus this part. It is sure less than from 1 to 2 direct.